Hello, my fellow mathletes. Root Beer here with question number 2 in Part B, that's the written portion, of the 2015 Senior Contest. Got 4 parts here, just like last question, question number 1, I guess. So 2a, we just jump right into it. If f of x is equal to x over x minus 1, so we got ourselves a function, and we can't put in 1 here, otherwise we'd divide by 0, and that wouldn't be very good. So there's our function. It takes in an x, and it transforms it into x over x minus 1. Determine all real numbers r that aren't equal to 1, for which f of r is equal to r. Alright, well, we got just an equation here to set up, so let's work it out. Let's set up, we know what fr is. We can write that out. So we want fr to be equal to r. Well, that's r over r minus 1. So we can multiply by r minus 1 on both sides. And we'll get r is equal to r squared minus r. We can bring the r over here, so we get 0 is equal to r squared minus 2r. And that's r minus 2. So r is going to be 0. Or r is going to be 2. Alright. And what can we do? We can even double check that. Here's our function. What happens if we plug in 0? We get 0 over minus 1. That's 0. What happens if we plug in 2? We get 2 over 2 minus 1. So we get 2 over 1. Well, that's 2. That definitely worked out. Great. We've got our 2 numbers here, and they both work. You might be a little hesitant to include the 0, but it's not 0 that this function doesn't work for. It's 1. Okay, B part. We've got the same function here, still not defined at 1, that's fine. Show that f of x is equal to x for all real numbers. Well, the easiest way to do that is just leave x in. Don't show it for 2, don't show it for 3, don't show it for 4. Show it works for all numbers. So let x be an arbitrary number. Then f of x is f of, well, what's f of x? It's x over x minus 1. What's f of x over x minus 1? Well, f tells us whatever we do, whatever we take in, we put that on top, and then we subtract 1 from it and put that on the bottom. So the number we took in was x over x minus 1, so that goes on top. And then we have x over x minus 1 minus minus 1 on the bottom. Well, on the bottom, let's get ourselves a common denominator. The top will stay as it is, but we'll get x minus 1 over x minus 1. So now we have a common denominator in the fractions on the bottom. We can combine those. We got x minus 1 all over x minus 1. Then we get x over x minus 1 all over x minus x is 0 minus negative 1, it's 1. Okay, and now you can either cancel out the x minus 1s or you can invert and multiply. So we invert the bottom fraction and we multiply, and when we do that, then these numbers cancel out, and we're left with x over 1, which is x. And we put a little box to show, hey, we did what we were told to do. So f of x is equal to x. And we just showed it. We kept x in there. We just took this statement, f of x, and we resolved it by saying, what does f of x mean? What does f of x minus x over x minus 1 mean? That sort of thing. I have a feeling this space won't be big enough for C, so let's flip over and take a look at C. Suppose that k is a real number. We got a new function here, g of x, and that's 2x over x plus k. And we don't want to divide by 0, so we're going to say x is not equal to minus k. X is not negative k. All right. Determine all real values for k. So we sort of have a family of different possibilities. Depending on what k we choose, we get a different g of x. We're asked determine all real values of k for which g of x is equal to x for every real number x with x not equal to negative k. And g of x not equal to negative k. Okay, all right. Well, I know what g of x is in terms of x and k. So then I should be able to figure out what g of x is, set that equal to x, and see if I can work out the values of k that work there. So we want this property to be true. Let's just expand and simplify the left-hand side. That's g of 2x over x plus k. We want all that to be equal to x. Well, what's g? G is the function that takes in something, doubles it and puts it on top. And then on the bottom, we put whatever we took in, and we add k to it. And we want that to be equal to x. All right. So, same as last time, we got some stuff to resolve on the bottom. With the 2, we can get a 4x over x plus k. I have a feeling some x plus k's are going to cancel out in a little bit. 2x plus k times x plus k all over x plus k. So now these two, just like we could invert and multiply, and they'll still cancel out. So we get 4x over 2x plus kx plus k squared is equal to x. That's what we want to be true. We want all the values of k that make this work. So 4x is going to be 2x squared plus kx squared plus k squared x. 4 minus k squared x is equal to 2 plus k x squared. And we want that to be true for every value of x. What are we to do? Let's bring it all over onto one side. So we've got 2 plus k x squared plus, we'll just rearrange it inside here, k squared minus 4x. Oh, k squared minus 4, that's a difference of squares. So I'll write this one as 2 plus k x squared plus, now we've got k plus 2, there's k plus 2 up there, k plus 2 here, and then we've got k minus 2, we've got x. So I can take out a k plus 2, I can take out an x, and then I'm left with x plus k minus 2. Okay, and this has got to be 0 for all values of x. Unless x is negative k or g of x is negative k. Okay, so this has to be true. If the right-hand side isn't a constant 0 function, then it is a quadratic of some sort. Did I already write some on the other side? Nope, okay. So it's a quadratic of some sort. Which only has 2 roots. X equals 0 and x equals 2 minus k. So if the function on the right isn't just purely 0, then it's a quadratic with some leading coefficient that isn't 0, and we'll only get 2 roots. So this tells us k plus 2 has got to be equal to 0. And that's the same as saying k is equal to negative 2. Okay? So if we look on the right-hand side here, this expression has to be 0 basically no matter what x I put in. There's 1 or 2 exceptions. X can't be negative k, that sort of thing. But on the whole, we can find dozens of numbers that would work. And we'd have to plug in x equals that number on the right-hand side and still have it end up being 0. The only way that can work is if one of those 3 terms, one of those 3 factors, is always 0, that it doesn't matter with respect to any of the x's. 2 of those factors change based on what x is, and so they can be non-zero. Both of them can be non-zero at the same time, and yet we still need to get a 0 out as our answer. So it's got to be k plus 2 that is always 0. And that means that k is going to have to be negative 2. And that's the only one that can work. Okay? So, we get k is negative 2. And in that case, we're all set. So we determined all real values of k. We got them all. It's got to be k is equal to 2. Okay, now we're on to D. Suppose that A, B, and C are non-zero real numbers. Define h of x to be ax plus b over bx plus c. This is actually reminding me of, okay, if you're watching this, you're probably in high school, but if you go on further in math, you might eventually go to university and study math and enter a subject called complex analysis. These functions that we're defining, the f of x, the g of x, and the h of x, are very similar to, what are they called, Mobius transformations from complex analysis, which are really cool, and I do recommend you look into them if you get a chance. But basically, complex numbers, you probably know what those are at this point. There's a great way to view complex numbers as a nice plane, sort of like the Cartesian plane. But there's another way to view it as sort of a sphere, with infinity at the top and 0 at the very bottom. And the equator is actually all the complex numbers that have an absolute value of 1. And there's a great way to convert between the two of them, stereographic projection, a whole bunch of fun stuff. Complex analysis is really, really cool. But what these functions do, these Mobius transformation functions, they're defined for all complex numbers. And what they do is they basically take this sphere and they rotate it different ways and they flip it inside out. And it's really cool. They're basically all the really nice transformations. They take lines and turn them into circles. They take circles and move them into different circles. Really nifty stuff, so I recommend you try and take a look at them. I'm pretty sure they're called Mobius transformations. I doubt that's going to help us with this question, but it's still just something that my memory got jogged, and I thought, that's kind of cool. I wonder if whoever made this question was looking through some old complex analysis books or something like that. Sometimes that's what happens. So, we got a new function, h of x, ax plus b over bx plus c. And this is defined anytime that x is not equal to negative c over d. C over b. Just make sure that the bottom isn't 0. Determine all triples a, b, and c, again, of non-zero real numbers, for which h of x is equal to x for every real number, basically except for these 2 exceptions. Well, we can do exactly what we did before. We had g of x is equal to x. Now we've got h of x. And that'll get us a whole bunch of a, b's, and c's. And we'll probably get some expression equals to 0. And there'll be certain choices, certain relationships amongst the a, b, and c that ensure that that is satisfied. All right. So we want h of x is equal to x. H of ax plus b, we're going to have to be careful because we're starting to add in more things. I just want to make sure all the algebra goes smoothly. So h is whatever we have, we multiply it by a on the top. So this is what we took in, we multiply it by a, and then we add b. Divided by, with b, multiply whatever we took in, whatever the input for the function was, plus c is equal to x. Okay. So we're going to shoot for a common denominator of bx plus c here. So we've got a squared x plus ab over bx plus c plus b squared x plus bc, multiplying b by bx plus c, all over bx plus c. But in fact, we can, they're fractions, so if we have a common denominator, to add them, we just add the tops, and it keeps the same common denominator. And that's all over. We're still going to get a bx plus c here, but now we get abx plus b squared plus bcx plus c squared all over bx plus c. Okay. Those ones will cancel out. And we can multiply by abx plus b squared plus bcx plus c squared. We multiply that by x. And we're left with a squared x plus ab plus b squared x plus bc is equal to x times abx plus b squared plus bcx plus c squared. Alright, so we'll have a quadratic on the right-hand side, a linear thing on the left-hand side. We'll bring it all over to the one side. So what do we get for our x squared? So we're going to get 0, abx squared, so it's ab plus bc x squared. So already I'm thinking of taking out a factor of b. Maybe b equals 0 is the only condition or something like that. I don't know. So that's where we get our x squareds. That's fine. Then we have b squared x, c squared x, minus a squared x minus b squared x. Okay, b squared plus c squared minus a squared minus b squared x. And you notice right away these b squareds are going to cancel out. Okay, and then what's the linear term? It's the stuff, it's all the constants from the left-hand side. AB plus BC. So we'll actually be minusing that. And there were no constants on the right-hand side because everything got multiplied by A. So AB plus BC. Well, for this to be true, because we do have to explain ourselves, if this is true for almost all x, then these coefficients, just like in the last one, coefficients must all be 0. If they weren't, then we're looking at a quadratic or a linear or a constant function. And no matter what quadratic or linear or constant function you're looking at, unless they're identically 0, you can find a value of x that makes them not 0. You can find an infinite number of values of x that make them not 0. And that's far more than the couple of exceptions where the function just isn't defined that the question has told us about. Okay? So the only way to make this work is the coefficients, the thing by the x squared, the thing by the x, and that constant term, they've all got to be 0. And that gives us 3 brand new equations to work with, and that's where we're going to get our relationships between the a's and the b's and the c's. You know, we can solve for all of them in terms of a, and that'll give us a nice way to express our triplet of a, b, and c. Okay? One thing we should keep in mind, however, is that a, b, and c have to all be non-zero, or is it just one of them has to be non-zero? I can't remember. So a, b, and c are non-zero real numbers. Okay. So maybe my prediction of b equals 0 won't cut it because that wouldn't work. So we get, I'm going to do this on the next page just because I want to have room to manipulate them. So, AB plus BC has got to be equal to 0. Another way to write that is B times A plus C is equal to 0. And then in the other one, C squared minus A squared has got to be equal to 0. Another way to write that, C squared is equal to A squared. So in this case, C is plus or minus A. Nifty. And then B, the last one is just AB plus B squared, or AB plus BC is equal to 0. So another way to write that is this. Okay. So what can we get? What could make the first equation, and by extension the second equation, 0? So that occurs only if B equals 0 or A is equal to negative C. But of course, this one's not allowed. A, B, and C, none of them are equal to 0. Non-zero real numbers. So B can't be equal to 0, so that's not going to work. So the only choice we have is A is equal to negative C. Fine. Okay, to make the second one true, well, we already sort of solved it. So this is true only if A is equal to C or if A is equal to negative C. Okay? But all the equations have to be true. So either A is equal to negative C and A is equal to C, in which case, these two both imply that A and C are 0, and that won't work for the exact same reason. So the only thing we can the only condition we need is A is equal to negative C. The only condition is A is equal to negative C, or I guess A came first, so let's say C is equal to negative A. The triples, A, B, C, which give h of x is equal to x, are of the form, we have any choice of A as long as it's not 0, and we have no constraints on B other than it can't be 0, and C has to be negative A. We'll just make the note A not equal to 0, B not equal to 0. And those work. At least they should work. And we can even double check, I guess. Because what did we get in C? C, we had G of, actually in both of these, f of x is equal to x, and our A would be 1. B is, f of x isn't of this form. Okay, so that's just another function that happens to have f of x equals 0. Same with g of x. It's not exactly of this form either. Oh, I got all excited for nothing there. But I suppose if we wanted to, we could double check, couldn't we? We could say, 1, 2, and negative 1. So h of x is x plus 2 over 2x minus 1. And then h of x is x plus 2 over 2x minus 1 plus 2 all over 2x plus 2, 2x minus 1 minus 1. I'm beginning to regret doing this already. We'll have 4x minus 2 over 2x minus 1 all over 2x plus 4 minus 2x minus 1, so that'll be plus 1, over 2x minus 1. Those will cancel out. Then here we'll have 5x over 5, which is equal to x. So this is a good check. Nice. Alright, so we checked our answer. We didn't need to. We've got a, b, minus a, and those are the only ones that will work. And that was after the only condition that was a and c need to have opposite signs, as well as non-zero. Now, if I remember correctly, I think you did lose a mark if there were some cases, like b equals 0 would have definitely helped you out, and that would have given cases, but that wouldn't have been any of the triples we're asking for, because b can't be 0. I do think when we marked this, you did lose a mark for that, because I remember this because at our local math program, every couple of years or so we get like a really, really good student, and we are very interested in what they do. And I remember I was asked to take up this contest the week after they wrote it, so I had to figure out a whole bunch of solutions and everything. And this student, he was so good. He doesn't really come anymore, but to the program, because the stuff that we do is child's play to him. But he managed to actually show up for the first 5 minutes, and he just quickly spoke to me before I got everything started and asked, what do you think the answer was for this one? This was my answer to this. Do you think I'll lose marks or anything? And he actually, he only lost 1 mark on this whole paper, as I recall, and that's because he had a 0 answer. I think he said a 0 minus a is a possible response, a possible set of triples. Okay, so you do. That's just another note for you guys to read the questions carefully, because otherwise he would have had a perfect paper, and that's a shame. But 99% is still great. Okay. Yeah, I don't think I have anything left to say. Question 2 is nice. A bit messy in terms of the amount of algebra manipulations we had to do, but that's not a big deal. And I'm looking forward to question number 3 on this contest. So join me for question number 3 in the next video, and I'll see you then.